In the last class, we have read that the electric field stress of a underground cable with respect to the relation with voltage was like this: V upon X ln of capital R upon R. Okay, so this was our cable, and this cable has a core with radius R, small r, and your sheath or the insulating material with respect to the center of the core has the radius of capital R. So if we find out the electric field stress at the surface of the core, we can write on core, okay, on the surface of the core. What we can write, the electric field stress on the surface of the core, we will replace X with the radius, so we will write it V by small r ln of capital R by small r, right? Similarly, on the sheath, or you can also tell that on the surface of the insulating material here, the electric field stress will be capital R. Just replace X by capital R. So this will be the relation. So here, if you can see, the relation of electric field stress was inversely proportional to the distance or the radius, you can say. So if you draw the electric field stress graph with respect to the distance or the radius, so the core radius is quite small and your insulate or surface radius will be more, so electric field stress will be more at the core and it will be very less at the surface. So the curve will be, if we draw the curve, it will be a rectangular hyperbola. We have discussed this in the previous class, right? So if you take out the ratio of electric field stress at the core surface and the electric field stress at the insulating surface, you can get a relation of capital R divided by small r. Okay, so we can tell that the electric field stress will be more at the core surface and it will be less at the. So one numerical is that there is one single core cable and is of single phase supply, and it has 6 kilovolt 50 hertz cable, and we need to calculate the electrostatic stress at core and the sheath having radius 1 centimeter, and this radius is the core radius and this is the 2.5 centimeter. Okay, so this is your 2.5 centimeter. So 2.5 centimeter is the radius, or that is the insulating surface. So just make sure that electric field stress, so this quantity which you are calculating, and we don't want any RMS value of this. Okay, if it is given that you need to find out the electric field stress, and if it is not mentioned that whether you need to find out the RMS, then you always think about that you need to find out the maximum stress. Okay, so by default, if it is not mentioned RMS, you have to think that it is a maximum stress. Okay, so maximum stress means what? So if you see the formula, there was voltage upon small r ln of capital R upon R. So this quantity voltage must be maximum voltage. So this 6 kV is the RMS. So maximum of 6 kV will be 6 root 2 and divided by your 1 centimeter. Okay, ln of 2.5 upon 1, and the unit will be kilovolt per centimeter. Remember this. Similarly, if we need to find out the maximum stress at the surface of the insulating material, and that will be 6 root 2 and divided by 2.5 ln of 2.5 upon 2.5 upon 1. Okay, the unit will be kV per centimeter. So always remember, by default you need to have the maximum stress. So here we will be discussing about the most economical core radius design. Okay, that means if you see the cable, you need to find out the economicity of the cable with respect to the core radius. That means अगर आपको एक केबल बनाना है तो आप किस रेडियस का केबल कोर चूज करोगे ताकि आपका ओवरऑल जो इकोनॉमिसिटी है यानी आपको फायदा मिलेगा with respect to the life of the material, with respect to the stress on that material. So basically we are more focused that we should get minimum stress, electrostatic stress, minimum electrostatic stress, that is it. Okay, और ये मिनिमम कौन से रेडियस पे मिलेगा वो वही मुझे पता करना है. सो एज वी नो that we have a relation that E at R, that is the core radius, and that has a relation V by small r ln of R by R. Okay, so we want this quantity, this electric field should be minimum. For that minimum, we can have the minimum value of this quantity. Okay, and we can operate at very low voltage also to have minimum stress, but this is a one of the constant. This is constant and this is a limitation for us. So we can't operate at low voltage just to get low minimum stress. Okay, so what other parameters are this? So mathematics can change, can see, or can make us see the relation in this perspective. E of R have some constant, we can make it as a constant and divided by a term that has a function of R. Okay, so this is a function of R. So if we want the electric field stress to be minimum, okay, so this quantity should be, function of R should be maximum. So how to get the maximum of that? F of R is R ln of R by R. So for any quantity to be maximum, differentiate this with respect to R and equate this to 0. So you will get the maximum value of this quantity. So once you get the maximum value or maximum condition, and you can say that at that point of time you are getting most economical core radius. Okay, so I hope you know the differentiation and you can equate it. So you will get, I'll directly write the answer. R by small r will be equal to E. And what is E? E is 2.718. Okay, so this radius, capital R radius, will be 2.718 times your core radius. Okay, so this is the economic condition. So if you want to design the economic core radius, so try to use that the sheath radius must be this, like this, or sheath radius must be 0.368 times of R. So this is one of the most important relation. You find out, you do yourself, and you can find out. I will ask this in exam. Okay, prove it. So that's why I have left for you. So now we will be discussing on the capacitance of single core cable. So capacitance, you might be knowing about that there is two plates, and one is at some potential, positive potential, and the other is at a negative potential. Then only you can have that capacitance. So whenever this condition comes, there will be an capacitive effect. Now, if you can see in the cable, I am just putting a single core cable, and this cable has a one core, and this core is operating at a particular voltage, right? This core is operating at a particular voltage V, but the outer surface of the core is at ground, right? Underground cables. So what we can see is that there is a capacitance. The first surface or the core surface is at potential V, and the other is at ground potential, that is 0. So you can expect a capacitance of the sheath. So what can you say about the capacitance of the sheath? Capacitance of the sheath can be defined as the charge it possesses per unit volt, right? And in the previous lectures we have find out that your voltage was equal to Q upon 2 pi epsilon naught or ln of r by r. We have integrated this, right? Like we have seen the formula, v is equal to integration of e x dot dx, and from we have integrated from r to capital R, and we got this, right? Just to make sure. Now if you see here, if you find out the capacitance, C is equal to Q by V. Okay, so if you just reshuffle and just put it in place, so you can get the capacitance value as C is equal to 2 pi epsilon naught, and you, with respect to the permittivity of air, I am putting it here, so I am putting it epsilon naught upon into epsilon naught relative permittivity, and that is divided by ln of r by r, right? So this is the capacitance, and the unit will be farad per meter, right? Farad per meter, or simply you can say, oh sorry, it should be not farad, it's simply farad, not meter. Okay, because the ratio, it is a ratio, so it will cut down, I hope so. So okay, just remove this. So this is the capacitance of your sheath. This capacitance we are actually talking about. Capacitance is 2 pi epsilon naught relative r ln of r by r. Similarly, we can expect if there is a capacitive effect here, there will be a charging current flowing, right? Charging current will be flowing. That is, this charging current we can, I can say as IC. And what IC can be? IC will be the charging current, can be your voltage upon reactance XC, right? And what is XC? XC is V upon 1 by omega C, right? And this C is nothing but your, you have just calculated, this C is here, this. So your charging current is nothing but omega C into V. So I'll give one numerical on this, and you have to solve it, and you have to tell me the answer in your, in the chat box of Google Classroom. Okay, so this is the one of the numerical here. A single core concentric cable of 5 km long has a capacitance of 0.2 microfarad per kilometer. The relative permittivity of the insulating material is 3.5. So here 3.5, that means it is given as epsilon naught. Okay, epsilon naught. It is giving epsilon naught r is 3.5. And the next thing is, it is given that the inner conductor is of the diameter 1.5. So it is not given the radius of the conductor. It is telling you about the diameter of the conductor. Okay, and the cable operates at 66 kV. Okay, 66 kV, make sure it is 66 kV, 50 hertz. So you need to find out the inner diameter of the outer conductor. That means you are actually going to find out the r, 2 of r, 2r. They want 2r from. Okay, and next here it is mentioned that the RMS voltage gradient of the surface. So it is actually asking RMS voltage gradient. That means it is asking E. Okay, E, but surface of inner, that is E of R it is asking. And then it is asking about the RMS value of the charging current. So it is asking about IC. So I hope you try this problem. It's good problem, and you write your answers in the this Google classroom. Okay, this is one of your assignment. I will match it and I'll upload the answer. Okay, in the next class. Thank you.